Hello friend, welcome to my new videos on my channel. In this video we are going to talk about NVIDIA CUDA C++ platform, which is kind of cool because this is what making all the AI magic happen underneath. And we have to take a look at this one. We have to be, as I say always in this channel, we have to be in the next wave as fast as possible. And even though we have this platform being a little bit mature, it's been around since 2010, so 2010. So we have like close to we're in 2024, so we have close to more than a decade of development, which is kind of cool because we have at least a mature system and framework that we can review, so we can analyze and see if we can if we need to include it in our next skill. I think CUDA++ it needs to be in one of your next skill to learn, and that's why maybe I'm going to include in this channel some of the learning process that I'm being having with the great platforms. So let's go over the blog post. I will try to explain my ideas, my personal knowledge about this, um, all the research that I've been doing about CUDA. And I hope you interact with me and share some knowledge here and and share your comments below, okay? So this post is a super simple introduction to CUDA, the popular parallel computer platform and programming model from NVIDIA. I wrote, this is important. This concept is important. Parallel computing platform and programming model. So we have a platform and a programming model. We have a way to program these new challenges and algorithm and ideas, right? And we have also a computing platform that was developed by NVIDIA. Okay, I wrote this post, the previous post, and its introduction on CUDA in 2013, and has been popular for over the year. But CUDA programming has gone easier, as they say. A GPU have gone much faster, which is true. So it's time for an update on that introduction. Okay, CUDA C++ is just one of the ways you can create massively parallel application. It lets you use powerful C++ programming languages to develop a high-performance algorithm accelerated by thousands of parallel threads running on GPUs. Okay, this paragraph here encloses the main idea of this video. So you can use C++, you can use this platform to enable high-performance algorithm accelerated by thousands of parallel threads running on GPU. And as we go explaining the whole tutorial, I'm going to share with you why this is so powerful. Many developers have accelerated their computation and bandwidth on replication this way. So right now we are in a computation intensive area and a bandwidth intensive area. So every application and the most important application, GPU, the new language model of AI, and are data intensive. So that's what I think one of the most important book you have to read is Data Intensive Application by Martin Fowler. It's kind of on my back. It's here, Data Intensive Applications. This one. You have to read this book. Happening with my internet. Oh, Martin Kleppmann. I'm sorry for the last name. So you have to understand this book. It's a dense book. You don't have to go over all the books, but you please make sure you go over the most important technicalities here and you can review them. Okay, let's go back to the previous post. So including the libraries and framework that underpin the ongoing revolution in artificial intelligence known as deep learning. So you heard about CUDA and you are interested in learning how to use it in your own application. If you are a C or C++ programmer, this blog post should give you a good start. Okay, I think this blog post will give you a start even if you are not C++ programmer, because the code that you will see here, which is the example we are going to use to examine the advantages of this parallelism computing, is please don't be scared if you are a web programmer with Python. The code is straightforward, and I'm going to explain with you for you can understand it. To follow along, you will need to computer with a CUDA capable GPU. So if you don't have a GPU, you can also enable one virtual machine or something, or some load service provider on the on any cloud, from any cloud provider that has the GPUs. Okay, so you also need the CUDA toolkit. We are going to talk about the CUDA toolkit in a different video, which is kind of free, and it's cool because you can use it for free and you can play with that for free. So you have a computing intensive framework that works on GPUs, on NVIDIA GPUs. You can run it locally. You can also run it on the cloud provider. You have a CUDA toolkit, which is free, and you also have a Jupyter notebook that runs on the GPU in the cloud, okay? Which is important for you developer can play and can learn around all the edges and advantages of this technology. So this is the example code. I'm going to explain the sample code really quick. I went over several times already. So we have a C++ code, which includes the IO stream, input output stream library, and the math library. We are creating an addition function which accepts two pointers of the float, okay, float values to arrays, and we are basically adding these two values, okay. So here inside the main function, we are just adding 1 million values per array, okay, and we are initializing them, we are adding them, okay. This normally we run in the CPU, right? We check for errors and we delete the memory. Okay, we don't have that. So this is, remember, we don't have a memory collector here on C++. So, and we compile the process. Sorry, the code here, we compile it, okay, and we see that doesn't have any error, and now we are going to start introducing the few changes for see how CUDA plays an important um, idea on the parallelism. So let's go. As suspected, it prints that there is no error in the summation and then exits. Now I want to get this computation running in parallel on many cores of a GPU. It's actually pretty easy to take the first step. And yeah, yes, indeed, because you only have to add the global specifier. First, you have to turn our add function into the function that the GPU can run, call it a kernel in CUDA. To do this, all I have to do is add the specifier global to the function, which tells the CUDA C++ compiler. And this is what is important. You have a compiler, you have a profiler, you have libraries to help you develop this, and you also have a runtime. Okay, so you have everything. So they give you everything. This is function that runs on the GPU and can be called from CPU code. Okay, with this simple specifier, as they name it, you can use the GPU, and you can use this piece of code in the GPU. So this piece of code will be running on the GPU level, but still can be used from the CPU. So the general code will be run on the CPU, and this part it will run it on the GPU. This is what I understand. Let's continue. These global functions are known as kernels, and code that runs on the GPU is often called device code, while code that runs CPU is host code. So we now enter a new in several new concepts. So you have a function in C++. This function can be converted as a kernel function if you just use the global specifier. And you can run a piece of your program in a CPU, which is they name host code, and you can run one piece of the code on the GPU, which they name device. They call device code. Kind of cool. Memory allocation in CUDA. Okay, this is the question we have to face now. So we have two GPU, two processing units working here for the same piece of code. So we have to share some type of memory for we can, or how we do this. So we have to share at least a piece of memory, right? So that's why they name this piece of memory unified memory. To compute on the GPU, I need to allocate memory accessible by the GPU. Unified memory. In CUDA makes this easy by providing a single memory space accessible by all GPUs and CPUs in your system. To allocate data in unified memory, you call this new function, which returns a pointer that you can access from the host GPU code or the device GPU code. to free the data. Just pass the pointer to CUDA free. Okay, so we can even play with the data between these two processing units in the same memory. Nice. I just need to replace the call to the new code above with the call CUDA malloc manage and replace call to delete the array. Okay. So this is how we allocate the data to the unified memory, and this is how we free the memory. Okay, so now it's an important concept. Finally, I need to launch the add kernel, which invokes in the GPU. CUDA kernel launches are specified using the triple angle bracket syntax. Triple angle bracket syntax. I just had to add it to the call to add before the parameter list. Okay, we're now just running a function kernel that's running one thread in one block and one thread, and has the same structure on the parameters. Okay, so we haven't changed anything. We just add a new syntax here. Easy. I get into details to what goes inside the angle brackets pretty soon. For now, all you need to know is that this line launched one GPU thread to run this function, the add function. Just one more thing. I need the CPU to wait until the kernel is done before it accesses the results, because CUDA kernel launches don't block the calling CPU thread. To do this, I just call CUDA device synchronize before doing the final error checking on the CPU. Here's the complete code. Okay, let's review the code now together with these new changes. We have the same function that we had before. We just added the global specifier, and we have the memory manage functions and also the CUDA free manage. So here you can profile it with one command line that CUDA toolkit provides you, and now we're going to explain how the threads works. In the next video, we are going to explain how the threads works and how to improve the performance of this simple algorithm using blocks and threads. And for that, just stay tuned and see you in the next video.